The estimate at complete for time works best within a context. Statistics give context to the estimate. They set plausible high and low bounds for duration estimates. Here's how. Statistical analysis is based on building blocks. From earned value management, get the planned value and the earned value. From earned schedule, calculate the amount of earned schedule and the schedule performance index for time. We also need periodic SPIT. But SPIT from real projects looks like this. That's the wrong shape for the most common statistical techniques. However, if the natural log is applied to periodic SPIT, it's transformed to look like this. That's the shape we're looking for. Here's log data for the example. Bell-shaped curves like this support common statistical techniques such as sample mean, variance, and standard deviation. Let's apply these techniques to the log data. First, calculate the sample mean. Next, calculate the sample variance. Then, calculate the sample standard deviation. We'll use statistical building blocks to set duration bounds. Let's start by identifying plausible limits for schedule efficiency. We do that because efficiency drives duration estimates. If we know the efficiency, we can infer the bounds. To find plausible limits, take the sample mean and adjust it with plausible dispersion. Plausible dispersion breaks down into score, swing, and size. The score is the distance a given point lies from the mean. That's here and here. The distance is measured in standard deviations. Given a score, we can infer the area under the curve. Given the area under the curve, we can infer the score. Here, what's marked out is 95% of the area under the curve. For normal curves like this, the score is 1.96 standard deviations on either side of the mean. Normal curves like this work best when sample size is large. They don't work well for projects. The sample size is too small. For projects, a different bell-shaped curve works better. It looks like this. As the dotted lines show, these curves have fatter tails. Such curves were developed for industries that require small samples, also known as tests. So they're called test curves, or T-curves for short. Sample mean, variance, and standard deviation are identical for both curves, but the area under them is distributed differently. So T-scores differ from normal scores. Here, the T-score is 2.57 as opposed to 1.96 for the normal score. Note also that the number of measurements is important for T-scores. The smaller the number of measurements, the longer the distance is from the mean for the same area under the curve. Why apply the T-score? We want plausible values for the bounds. Outliers are not plausible values. We exclude them by narrowing the area under the curve from 100% to 95%. Here are the T-scores for the example. Next is the swing. There's a natural swing in measurements depending on sample size. Bigger samples mean less variation. How so? With the bell curve, as measurements are added, proportionally more go to the center. That's what causes the peak in the curve. If more go to the center, proportionally fewer go to the tails. The higher the peak, the narrower the spread. The swing is expressed mathematically as the standard deviation divided by the square root of the number of measurements. Applying the swing to the example gives us these results. The last factor is size. Statistics compensate for small sample sizes with the following formula. We can interpret the formula specifically for earned schedule. In earned schedule, there's one and only one measurement per period. So, the uppercase N equals the total number of periods to be earned, that is, the planned duration. And the lowercase n equals the number of periods actually earned, that is, the earned schedule. That leaves the final term, What takes the place of the number 1? It's the unit value of earned schedule. That is, the earned schedule divided by the current period. Here are the results from applying the formula to the example. Finally, scale all 3 factors to one another. Then, apply the factors to the mean. Adding them to the mean gives the high efficiency limit. Subtracting them from the mean gives the low efficiency limit. Here are the limits for the example. We can't set the bounds yet. There's one item still open. We need to transform logs back into SPIT. To do that, we use the inverse of a log, an exponent. An example explains how exponents fit in. For an exponent, you take a number as base, say 2, and you raise it to a power, say 4, to get a result that's 16. Logs do the reverse. You take the log of a result, say 16, for a base, say 2, and you get the power that produces it, 4. We can go back and forth between these two expressions because they are equivalent. Applying this to our case, we started with SPIT and took the natural log of it. The natural log has an implicit base that we'll call x for now. Statistical analysis of the log data produced efficiency limits. They're still in log form. To transform them, we take the base x to the power of the limits, and that gets us back to the SPIT. But what's x? A full answer calls for a separate video. The short answer is, it's a magical number like pi, but one that's not quite as famous. It's the number e, which is approximately 2.72. So we raise e to the power of the limits, and that gives us the SPIT. Here are the SPITs for the example. At last, build the bounds. Use the classic formula for the EACt, the planned duration divided by efficiency. For the EACt high, use the SPIT minus, that's the low limit. It signifies less efficiency. Less efficiency means longer duration. For EACt low, use SPIT plus, the high limit. It signifies more efficiency. More efficiency means shorter duration. Here are the bounds for the example. Thus, we've used statistical analysis to set plausible high and low bounds for duration estimates. Combining these results with the nominal estimate and graphing them gives us this. The picture shows how bounds give context to duration estimates. For now, let's summarize building the bounds. It starts with statistical building blocks, the sample mean, variance, and standard deviation. Along with t-scores, they are applied to schedule efficiency. The results are then used to identify the limits of efficiency. The limits must be transformed back into SPIT through their inverse. Finally, SPIT is used in the classic formula for the estimate at complete for time. It sets plausible bounds for estimated duration. For more information on this and other earned schedule topics, here are some references.